From the ground up, let's check out how a spacesuit is made. Let's first start with the neck ring. So this consists of a few parts: a O-ring, the mounting flange, this is the socket side, and neck restraint cables that are attached on welding points here to help hold the helmet down and the neck ring down. This is made from a pressure cooker this is the lid section, top part, that I added some vertical flange to create a mounting surface for the band clamp, the hose pipe clamp, to hold on the system. It is attached by glue for sealing purposes. It is attached by a band clamp and then backed up by a bunch of rivets here. That's enough to have integrity, held 10 or so PSI. Next thing on here is the cable system. This looks really busy, but it has three functions: to hold the arms in so you don't bust your shoulders. It keeps the neck ring down, and then goes around the crotch to the back end of a hold-down cable to hold a system in tension. These two air ports here are what I call the high flow ports. This one here is the input. It goes into a distribution 3D printed part that blows air up into the helmet. This one is the return. It just takes suit gas and brings it back into the scrubber. Now, speaking of gas ports, right here we've got ourselves an oxygen regulator. This is air. This is the gas in. This takes anywhere from 25 to 125 psi and turns it into the 0 to 5 psi to inflate the suit. This does go up here to the inlet port, so we've got main gas going into the helmet. This is a test port to add a gauge. That's not going to exist in the final suit design. This right here is an OPV. In this case, the light blue one will open at about 1.2 psi. This way, in case of a failure of the regulator where it gets stuck open, it won't burst the suit as easily. This can still outflow that, but only barely. These two plugs here are for water cooling. There's no inner output. They're just a loop, so that doesn't actually functionally matter at all. And right here is the all-important helmet hold-on cable. This takes a piece of strapping that goes underneath the crotch right here, and it helps hold the helmet down. When you put the suit on, you will take this, you'll put it through, and you'll tension this, and it brings the whole suit vertically from the crotch to the neck into tension. That's called a hold-down cable. Let's discuss gloves. It's the wrong side. I get that, but it doesn't matter in this case. Gloves will go on. They've got an O-ring, as you noticed. This is the glove clamp. It is applied around the glove like so and locked into place. This should be able to turn freely. No, it's not a bearing, but that indicates that this will fit in here cleanly. And you'll take this push pin, put it in, and do this. These may be swapped out for better retention later on. They're just kind of convenient for right now. And that allows for the glove. And the glove can still be twisted a tiny bit. Now, there is no bearing here. And once under pressure, it's much harder to turn. But you can grab, with your other hand, your wrist and then change the gloves to change from a moment like this to this or anything in between by just twisting your own arms kind of thing. The boots here are assembled as a two-piece structure. In here is a plastic ring, and the boot goes on the outside of the fabric. You got a ring here, fabric, with the retention fabric too, both the bladder and the pressure restraint fabric, and the boot on the outside. So you've got the inside of the suit facing the inside of the, like this, kind of U-shaped like this, facing the inside of the boot. This way you can get a really good tight seal. And then, of course, there's a band clamp on here, and then rivets to hold it in place to back up. And that is your boot. Now let's discuss the backpack. This device weighs around 45 pounds, and it contains the breathing oxygen and all the air parts necessary to make the spacesuit work. This is an oxygen cylinder. It holds 2,200 psi of oxygen, nominally, and it holds around 20 cubic feet of oxygen. enough for 7 hours, give or take. This is the primary stage regulator. This takes the high pressure and puts out about 50 psi. Included also off the side is a lanyard hose with a contents gauge. This shows the actual pressure in the tank, aka your runtime. To the left of that right here is this. This is the scrubber assembly from here to here. In here goes tons of pellets. Air comes in the bottom, goes up, and is pulled through by a blower fan, pardon me, on the top that removes CO2, helps remove CO2 by pumping the air throughout the suit. This is serviced by something called a BNC jack. It's a little plug here on the side, which is how you can unplug it. And then, of course, to fill up the container to add CO2, add pellets to remove CO2, pop it off like so. To reassemble it, put it back on, and then key in the latches, like so. And then, of course, you want to add power so your system works. Beneath that, thinking of power, are 2 batteries. Each one is about 200 watt-hours apiece, enough for 2 to 3 hours per battery of EVA time. Combined, 400 watt-hours, 6 hours max, probably closer to 4. And that powers the whole thing. About 80 watts goes to the chiller, and the remainder, 15 to 16 watts, goes to the scrubber fan. And it's all controlled by this, the chest controller. Left hand is the upper battery, right hand is the bottom battery. On your left hand also is a switch. This controls the scrubber. On the right hand, controls a 2-way switch that controls either the top or bottom battery being used for the chiller down here. That chiller keeps the user cool by circulating cold water throughout the suit using the pump right here. This pump takes cold water that is basically chilled by this through means of a refrigerant called R134A and a small intercooler. This draws about 80 watts. This is the vast majority of the current and power consumed off the batteries in the suit. And that is the suit, both the suit section and the backpack. Thanks for watching.